We are the only center can do those two facilities together. In entire Europe, probably there are few, and we are the leading one there. And we work with 36 UK universities and some other universities internationally as well. This is to particularly cater top-end semiconductors, research, and also outreach and technology. And India has some really good accelerators. It's not that they don't have, they have really good accelerators, but it is isolated and as you rightly said, not easily accessible to the academics or the industries, and also like they can do only one, whereas only one type of implantation, whereas we can do at different energy levels, right, from 1.25 MeV to 2 MeV to 6 MeV. So we have a huge range. We can cover from semiconductors to nuclear materials to space applications. We work on space solar materials. So there's huge wide materials and it is accessible. It's a pretty much like a national facility. When I started, it is accessible to all. IC world is full of materials, including the nice LEDs and etc. displaying in this. It's a material, gallium nitride LEDs. It's all material. Without materials, there's no life, including my glasses. There's no materials. And if you go to the Stone Age, people say Stone Age because it was earth abundant. Bronze Age, earth abundant material. Then Iron Age, earth abundant material. Silicon, sand, from there you get silicon out of it. Earth abundant materials. Can there be a two-dimensional material, the layered structures which we always proud of, giving the properties? Can this be earth abundant material? You need to have a kind of a translation agency. You need to have. Say for example, I am producing a material and I know that the material works really well. That's a proof of concept. That is, proof of concept is we call TRL, technology readiness level. So 1 to 3 is a proof of concept. I prove this is working in my lab. So what? I publish the paper and that paper will be adopted by some other Chinese agencies, etc. And they'll go. There are more mobiles than human beings in this planet. And it is going to go much further with AI, etc. Every house has 3 or 4 mobiles. And they realize that there are precious metals there? We should not be in an era of publish and perish. You need to publish and process into products. And that is where as I said, I think it's third or fourth time I'm saying, it's like taxpayers' money needs to be utilized and that people should see something coming out of it. When I compared Kerala with Switzerland, I think probably both are amazingly touristic place. Switzerland has IBM Research, or IBM Zurich.
Kerala
don't. The people will excite. You need to excite science, like Science Talk. You need to create excitement. That excitement is the one. More outreach needs to be done, pretty much like this. More outreach programs has to be done to ignite the minds of the young people. Okay, here it is the problem for you. Can you solve this? They challenge them. They like the challenge.
ഡീപ് ടെക് കൊമേഴ്സ്യലൈസേഷൻ, ക്ലീൻ എനർജി ട്രാൻസിഷൻ തുടങ്ങിയ ലക്ഷ്യങ്ങളിലേക്കുള്ള കുതിപ്പിൽ നമ്മുടെ മണ്ണും വെള്ളവും എത്രമാത്രം മലിനപ്പെടുന്നെന്ന് ചിന്തിക്കാറുണ്ടോ? സസ്റ്റൈനബിൾ ഡെവലപ്മെൻറ്റ് എന്നുള്ളത് റിപ്പോർട്ടുകളിൽ മാത്രം മതിയോ? നമസ്കാരം. ഏഷ്യാനെറ്റ് ന്യൂസ് സയൻസ് ടോക്കിൻ്റെ പുതിയൊരു എപ്പിസോഡിലേക്ക് സ്വാഗതം. നാനോ ടെക്നോളജി ഉപയോഗിച്ച് തുണിമില്ലുകളിലെ മലിനജലം ശുദ്ധീകരിക്കുന്ന സാങ്കേതിക വിദ്യ, ലിഥിയം അയോൺ ബാറ്ററികളുടെ പുനരുപയോഗം, അടുത്ത തലമുറ സെമി കണ്ടക്ടറുകളെ നിർവചിക്കുന്ന അയോൺ ബീം ആക്സിലറേറ്ററുകൾ, ഇവയെല്ലാം ലാബിൽ നിന്ന് വ്യവസായശാലകളിലേക്ക് എങ്ങനെ എത്തിക്കാമെന്നതിൽ വിദഗ്ധനായ പ്രൊഫസർ സതീഷ് കൃഷ്ണമൂർത്തിയാണ് ഇന്ന് സയൻസ് ടോക്കിൽ അതിഥി. UK സറേ സർവകലാശാലയിലെ എനർജി ടെക്നോളജി വിഭാഗത്തിലെ ചെയറും പ്രൊഫസറുമായ പ്രൊഫസർ കൃഷ്ണമൂർത്തി, സറേ, മാഞ്ചസ്റ്റർ സർവകലാശാലകളും UK അറ്റോമിക് എനർജി അതോറിറ്റിയും സംയുക്തമായി നടത്തുന്ന ദേശീയ ഗവേഷണ കേന്ദ്രമായ UK നാഷണൽ അയോൺ ബീം സെന്ററിൻ്റെ ഡയറക്ടറും കൂടിയാണ്. പ്ലാസ്മ ഫങ്ഷണലൈസ്ഡ് നാനോ മെറ്റീരിയൽസ്, സർഫസ് എഞ്ചിനീയറിംഗ്, സെമി കണ്ടക്ടർ പ്രോസസ്സിംഗ് എന്നീ മേഖലകളിൽ ഗ്ലോബൽ എക്സ്പേർട്ട്. കൂടാതെ നല്ലൊരു ക്രിക്കറ്റർ കൂടിയാണ്. സയൻസ് ടോക്കിലേക്ക് സ്വാഗതം പ്രൊഫസർ കൃഷ്ണമൂർത്തി.
Namaskaram and swagatam to all the viewers, and thank you so much for the invitation to be there, and also congratulations for doing the 100th show. Actually, this is very important. This
Now
science
this is
talk.
107th
Yeah,
episode.
over 100 shows, and this is really important for nurturing the younger minds and also taking science to the public. That's one of the reason I was passionate in delivering this or sharing my ideas, not delivering, sharing my ideas with you all of what is the current state of science and how it can go into deeper roots and change the policies and how taxpayers' money can be really utilized where the science can be realized to society. Thank you.
Thank you, sir, and we also appreciate your kindness to participate in person for the interview. So, you are the director of the UK's National Ion Beam Center, a national facility, not just a university lab. So, what does that role actually involve on a day to day basis, and how it is different from the academic roles you previously held in the career?
Yeah, I think I'll just quickly brush back my career. So I studied in a government school, pretty much in Nanganallur, a very small village in Chennai, and there is no what do you call. We sat in pretty much in sand, silicon that time, put it that way, and that's how we studied, and then journey towards Newcastle, did the PhD there, and then worked in NASA for a few years, and then taken up this role as a director of UK National Ion Beam Center. And it's a very interesting concept, particularly the UK government has put in. So they want scientists, academicians to interact with each other. How do they interact with each other? And they wanted to make sure the center should be accessible to entire UK at free of cost. It will be borne by the government, the cost. So that's a really good idea. And it is all peer reviewed proposals which we gave. So I kind of liking this concept, particularly the Ion Beam Center. So it started in, this is what, no, where there is a will, there is a way. So they started in a paint shop. The paint shop of this size, that is where the origin of the Ion Beam Center started. They're the two really brilliant scientists from UK. They say that I wanted to do something to the community of the accelerator physics. So they started doing that. Then they moved into university, and then they got the National Center. So what do we do? So it is pretty much, as you rightly said, even though I'm an academician, I'm pretty much like a CEO of a company because we run like a company. And we work with 36 industries, use our facility to do ion implantation and ion beam studies. And these are all very important in manipulating the semiconductor materials. And also, that is one type of ion implantation. And we have ion beam analysis. Ion beam analysis is pretty much like the eyes are here, and I put the glasses, then I can see better. So ion beam analysis is, that is the ion beam goes there and understands the chemical imaging and the mapping, etc., which cannot be done by any other means. And we are the only center can do those two facilities together. In entire Europe, probably there are few, and we are the leading one there. And we work with 36 UK universities and some other universities internationally as well. This is to particularly cater top-end semiconductors, research, and also outreach and technology.
So, what about the collaborations with the Indian universities or Indian industries with this Ion Beam Center?
So, the reason why I am here in Trivandrum is because we won a UK-India research grant funded by British Council from UK and also from Indian government. It is SPARC or DST, Department of Science and Technology, to do high-end two-dimensional material semiconductors with ICER Trivandrum. So it has been going for 2 years, and we are now doing some kind of outreach conferences to disseminate our results, to bring in experts from all over India and also some parts of UK as well, to get the network and the idea generation going to see what better we can do next. So that is why I'm here. And the collaboration with India is top in my list, and I think I have got close to about 8 to 9 UK India grants with almost all parts of India, right from Kashmir to Kanyakumari. So working on several aspects.
So, how does it feel to be an Indian at the helm of a UK national research facility?
Yeah, that's a good question. So it was a kind of a privileged position. And I think if I look at it, I'm the first Asian to be the director of the National Research Facilities. And I am happy and proud that rather than the tag on Indian, it brings a really good responsibility to do something new. And also, as I said, we always need to measure the outcome. So I'm very focused on how we measure the outcomes. That outcome can, so it's all boiled down to taxpayers' money. That is what we are. And how we are responsible for the taxpayers' money to get it back to the society by having a skills development, research excellence, and how I can gap the industry needs. And industry needs is very important because no industry will come if you do not offer them what is not available in the domain. So we always keep ourselves in the top notch of research and cutting edge technology. So I take pride of my team. We have a wonderful team of people with both technology and also experimental officers. We have huge quality assurance. So I'm learning quite a lot of new things to improve as well. So India is also part of my strategy to see how well we can work together, considering the new free trade agreement in place. So this will give us more leverage on the export control system.
How many Indians in your team or from anyone from Kerala?
Oh, good question. I'm the only Indian in my whole of my team as of now. So that doesn't mean that I am in the process of hiring. So we will see how it is. It's not the question of Indian, or it depends on who brings the right skill for us to match. So that is where I am.
Okay. Can you explain what is an ion beam? How does it differ from an electron beam or optical beam, like
Yeah.
laser, like that?
That's a good question. So its ion beam is it is pretty much like a very powerful laser systems. Okay, so and you have kind of particle accelerator. You have accelerator is nothing but accelerating ions at different velocities. And say for example, you all know what is periodic table of elements. So periodic table of elements, right from lanthanides to actinides, and then alkali metals, alkaline. So pretty much transition metals. So for each and every metal, in order for us to evaporate this metal and get deposited on the surface, we need higher energy. This cannot be done using laser. Laser can do, but it does in very small scale, like pulse laser deposition, and it has its own limitations. Whereas ion beam centers, we have about like 7 implanters of varying energy, and then we can also heat at higher temperatures, low temperatures, and we can play around with in the clean room as well. So we can pretty much implant anything in the periodic table of elements, which no other facility does that. So that gives us the platform to interact with industries. Industries come, say for example, in this quantum era, we are talking about we make quantum chips with indium phosphide, etc. There's certain compound semiconductors. They will come to us, and then they asked us to implant the particular material onto their system for faster optical communications. So which cannot be done by any other place. And we have been working with several decades with one company. There are quite a lot of other companies are also there. So we act as a bridge between academia and industry.
So, since you are working in this field and interacting with many industries, directing the National Research Center, what lessons we India can learn from this center? Because we also have particle accelerators in TAFR like research centers. I think it's only for academic purpose. So, how the industries or the semiconductor environment emerging at India now can use these facilities?
It's a very good question about, see, in India, I looked at what is available in India, and India has some really good accelerators. It's not that they don't have, they have really good accelerators, but it is isolated and, as you rightly said, not easily accessible to the academics or the industries, and also like they can do only one, whereas only one type of implantation, whereas we can do at different energy levels, right, from 1.25 MeV to 2 MeV to 6 MeV. So we have a huge range. We can cover from semiconductors to nuclear materials to space applications. We work on space solar materials. So there's huge wide materials, and it is accessible. It's a pretty much like a national facility. When I started, it is accessible to all. It's not for one. So if we can get into that domain, probably you may get better reach for the and India is huge. You need more than one national facility for India to cater this if you wanted to have a good high quality science, technology and skills needs to be developed. And if we come back again to uh, the most important thing which I would like to share is we play a huge thrust on quality assurance. QA is a major part. We do like each person does 53 times QA. That's I myself do the QA as well to make sure that the quality we deliver, quality of the material we deliver, quality of the process we deliver, every single thing we make sure that it is up to the standards. Say, for example, if you give me a recipe, like today I wanted to get some orange color in my trousers, and this size should be like about exactly like two dimensions, two by three dimensions, and also penetrate up to 5 microns. We do exactly what you speak, what you give, and because of the quality which we maintain, there's no change at all. So those things the industry likes that. Industry likes that exactly what I want, they can get it for, they can do it for us. So that's the reason they, and we have the tools. The UK government has invested close to 40 million pounds in our facility just for the equipments.
So whatever equipments or research centers we have, that should be accessible to all other research institutions as well as the industries first. And the second one is we should assure the quality,
Yeah, there are,
what the industry demands.
so the industry demands is like I have employed research liaison officers. These research liaison officers has to sell my products, what we are available, and how this instrument can answer your issues. So they will be working, they will be directly liaising with industries and bring the clients to me if the industries are not coming directly to us. So we have this good ecosystem we developed, and there is a separate project manager and others there. They will be also monitoring this whole work, how the ecosystem is really set well in such a way that the industry can work with us with ease. That is one thing. And for the access to the academicians, other universities, is very important that we give equal access to everybody. There's nobody like I also work with Oxford's uses my facility, Cambridge uses my facility, and also other low tier universities also uses my facility. So I wanted to give the access to good quality science irrespective of wherever it comes from. So the UK government has given us something called pump priming. It's a really good idea. The pump priming gives access to say about like 20 hours of beam time that can be given to a project that can nucleate and go into bigger things. So we do that. So we do that and promote that low tier universities. And then I really place a huge emphasis on gender development. So I would like to give more opportunities to all the other genders. That's important. So that's where we bring everybody inclusive.
Another curious question I would like to ask is that our human history transformed from Stone Age to then Iron Age, then Steel Age. Now we are in the Silicon Age for decades. So, do you see whether the silicon will dominate for another decade or any other material now challenging silicon's dominancy?
Yeah, I think you hit the nice silver bullet for me. So we started with Stone Age, then we went to Bronze Age, then we went to
Iron Age.
Iron Age. Now we are in Silicon Age. So you take the history. I see world is full of materials, including the nice LEDs and etc. displaying in this. It's a material, gallium nitride LEDs. It's all material. Without materials, there's no life, including my glasses. There's no materials. And if you go to the Stone Age, people say Stone Age because it was earth abundant. Bronze Age, earth abundant material. Then Iron Age, earth abundant material. Silicon, sand, from there you get silicon out of it. Earth abundant materials. Can there be a two-dimensional material, the layered structures which we always proud of, giving the properties? Can this be earth abundant materials? If somebody asks me, give me a like 10,000 tons of graphene, can we make it? When we talk about that scale, then it becomes that definite two-dimensional material era. And To answer your question, the silicon age will continue to dominate. I don't see a replacement for silicon. It is keep improving. There could be silicon and hybrid technologies, unless some type of a new material. Okay, graphene is a fantastic material. The Nobel Prize, Andrew Game and Kosti, both are good friends of mine, and then they got this Nobel Prize, and they did from there. There's plenty of other two-dimensional materials arrived. The recent one is Maxine, where different types of layered structures, we have different types of functionalities that can tune themselves into, we can tune easily them without a need of additional materials. So there are different, but can we make it high clear in a different volume? Because volume and scale is important. Can we produce that in a scale that meets the semiconductor industry's demands? That's a challenge. And that challenge is, I'm not saying it won't be answerable, but it takes time. It takes time, and it takes high intensive research and development to get into that stage. So maybe, I don't know whether I will see in my era, but maybe definitely it will be there.
So there may be a wide range of 2D materials from graphene to boron or any other
So graphene is
Maxine.
already there in the market. It's a specific applications like tennis rackets, and people are using in cement industries. So there are certain as an additives, not as a like silicon is like silicon is solar cells in your phones. So it is there everywhere. That is why it is a silicon age. Whereas, can I say 2D materials like a graphene age or something? It's difficult to say at this time. Even if an ambitious person will not say that, it's difficult. There are gold nanoparticles. These are all composition of paints. So we are talking about as if we discovered something, but it's already been there and proved in those areas. So we are reinventing the wheel, but the scale is not the same. Like, can we say it's a gold nanomaterial era? I can't say that. But however, there are specific applications. It is there.
Will you explain how does this high energy ion implantation and accelerator technology fundamentally alter the properties of these advanced materials and semiconductors? Whether we get new materials or we alter the properties,
So
physical
there are
properties.
two types of ion implantation we do. One is changing the electronic properties of the material and the systems. So we can create, say for example, you have some lattice there. Lattice is nothing but the atoms arranged in a periodical fashions. And then when I shine particular, say for example, helium ions or argon ions, argon is a gas, helium is a gas. So at the particular dose rate, if a particular dose is nothing but it's pretty much like a dose, light dose, particular dose, I can kick off the atoms and then create a vacancies or create some defects in the lattice. These defects particularly are important in changing the electronic properties of the system. So it tunes the electronic properties in such a way that I wanted the particular energy or light energy to be absorbed on this material so that it can act as an optical sensor for me. So that type of system which we work. Another type of material, another type of instrument which we have, which is unique to us as well, it is called single ion implant. Single ion, so we have a broad beam implant. Broad beam is pretty much like, say for example, I have a torchlight. If I switch on the torchlight, it is divergent. It gives, initially it starts like this and then it is diverges everywhere. So it's completely broad. So I have an ion implanter, which is a broad beam implanter that pretty much implants the whole surfaces. I have a single ion implanters. This single ion is, single is one, only one ion goes and implants on the surface and we detect only one ion. This is where the quantum technology goes. So in terms, say for example, diamond is a fantastic material. And in the diamond, we create defect centers called NV centers with only one ion. So one ion goes and hits the surface and then it dislocates that particular carbon and creating a vacancy. Vacancy is like void, there's nothing there. These vacancy centers are very important that can enhance the optical emitters. Okay, these optical emitters are good for quantum communications, to say it low. So we can do it in diamond, we can do it in silicon carbide. So there are many other interesting materials where we create this. So this is called NV centers, we call. So that is only with single ion implants you can do it in much better. And similarly, we can do hundreds of qubits quantum qubits. These quantum qubits are necessary for memories and the RAMs and encryptions, etc. And we are the only center in UK can do this. Apart from there's one in Manchester they can do as well. But in UK there are only two available. Two such systems are available.
You have considerable work on low-cost graphene-based solar cells, then and it is designed for decentralized production also. And you have already some research in photovoltaic cells also, that is sulfide-based thin film photovoltaic. So, what are the advantages of these cells, and also how much we can learn from these technologies, since Kerala is also giving so much importance to solar energy production to meet our energy demands.
Mm-hmm. So as I mentioned in the beginning of the talk, so I work with quite a lot with Indian universities. And this project which we are talking about, printing of graphene integrated solar cells, it's funded by Royal Society with a university called SRM. So our idea is to make flexible solar cells, and then we print the graphene and also the other materials directly onto the flexible plastics. And we were able to get decent efficiency, about like we are talking about 15% efficiency we got, but the stability is a question. So we are still a continuous improvement on the stability of these flexible solar cells which we are working through, and we need to introduce new buffer layers and also the binders as well. So there are researches happening between us and SRM on the other basis, but these kind of funding is, once it's done, it's difficult to again start because the funding continuity is not there. So we are working on an ad hoc basis now in this technology. Coming back to your critical question on Kerala solar programs, I think Kerala has a massive issues. Land is an issue for Kerala, and humidity and temperature is an issue for Kerala. And I was thinking that the floating solar programs, floating solar cells could be a really good option for Kerala government to see whether they can,
Since we
because
are
you have the water everywhere. So if you float the solar cells in water, and then what you do is you
solar powered boats we can have.
Oh, no, not only boats. You can generate the power with the floating solar cells. So you don't need a land. If you see Gujarat or Tamil Nadu or Andhra, they have massive land. So they put solar panels on the land. But you can put solar panels in water so that you stop the evaporation of water. We have those states use water for cooling, but you use the same water here for cooling. So you take multiple challenges out. But only thing is there are other issues will come on fouling, etc., anti-fouling agents which you need to put through the things, and then how you connect those cables together to the grid. So there are multiple challenges are there so that you don't disturb the water ecosystem as well, because fishing is another major industry in Kerala. So new solar, and there is massive research program is happening in Cochin, QSAT, and other universities and national institutes, but there is a gap in taking that research to the industry because of the other challenges are that the setup needs to change.
So, what lessons you give for commercializing these research gains from these universities?
Yeah, this is a very, very important thing which I find that we need to have a kind of a translation agency. You need to have. Say, for example, I am producing a material and I know that the material works really well. There's a proof of concept. That is, proof of concept is we call TRL, technology readiness level. So 1 to 3 is a proof of concept. I prove this is working in my lab. So what? I publish the paper, and that paper will be adopted by some other Chinese agencies, etc., and they'll grow. But can we harness this TRL3, take to industry, and prove it in industry setting it is working? Once you do that, then the industry says, okay, I want to make all these changes. Can you do? The universities cannot do. You need to have an intermediary there. So you need to have a kind of agency who has a lot of really good scientists and also business acumen to take this forward and make it as a scale, and then adapt to industry. Because industry will not make any investments unless they see that it is low cost, it is fit to the market. So that translating agencies has to be there in the ecosystem.
Kerala government already have such an agency called K-Disc.
No, I think I don't know about KDISC, but getting that agency right is very important because we are talking about scientists working there. So top-notch scientists. So um, these top-notch scientists will be working with business guys to make sure that it is the work which we are doing is can really go into low cost and high efficiency and fits to the requirement of the customer rather than going for publications and patenting. So that kind of mental change has to happen.
Then you also have some technology readiness or commercialization of technology for treating the wastewater from denim factories and other factories in Tamil Nadu with participation with PSG College of Technology. So will you explain that also?
So
Cleaning the water, because the Central Pollution Board report says that out of the 44 rivers, 32 are already highly polluted here. So what can we learn from you?
yeah, I think it's I'm always passionate towards um, giving back to community and society. And science for society is very important. How we socially oriented research that has direct benefit to society. So with this mind, we started working on catalytic materials. These are all semiconductor photocatalytic materials. These semiconductor photocatalytic materials reacts to light, visible light, and then organic reactions takes place, and then the material oxidizes, and then the organic material oxidizes, and then you get a clean water, H2O. Okay, in the process, we'll also generate tiny amount of CO2 in the atmosphere, but we do have really good quality water we generate by degrading organic pollutants. So that is what the project. And with the PSG as a partner, PSG College in Coimbatore, so we were able to use biomass. The biomass is plenty in India or in that part of the world as well. So we used biomass to decolorize the dyes first. So the biomass has a really good adsorbance. It absorbs all the colors, and then it leaves kind of a semi-transparent water that is good enough for me to pass the light through the system and also the catalysis through the system, and then to clean the water. So we were able to do this, and then we did this TRL 7 project with working with some textile industries. This is what we did. And this the learnings I had from this project went into something really big. So when I saw that we can do this in a small scale, why can't we do in a denim factory? Denim factory is denim jeans. So I feel that from the top to bottom, we are all contaminated with dyes. From the hair colors to my jackets, shoes, everything is dyes. And everything I'm polluting, that must be. Can we do something to this? I got a passionate scientist from all over Europe, because it's a European funding of 10 million. All the passionate scientists. So when we designed the program, we thought that we need to do end-to-end. End-to-end means where the material is resourced, how the material is deployed, how the material is recycled. And we also brought in AI as well to understand the sensor development, and then the heavy ion detections, etc. So that here are heavy ions and heavy metals are there in the textile industry. So we went a complete circular economy approach, and we deployed a low cost material, printed material onto wool. Sheep wool is amazing material. So when we started working with stainless steel, the cost was heavy. We coated the photocatalytic material on stainless steel. We coated the photocatalytic material on optical fibers. Everything was expensive. The industry says that no, we can't adapt this. Then sheep wool came. We put on the sheep wool. It works. And then it has higher surface area. And then we coated the nanomaterial on top of that, and it can clean up to 500 liters of water in one go. So that is deployed there currently in Turkey. The learning is, which I said, I cannot do this 500 liters immediately. There's a company called CPI Catapult. This Catapult helped us how to do the scaling up process. There are things which we were missing. They were They were hand holding us that you should do this different types of recipe you need to try in order to get it better. And the Catapult is partly funded by the UK government, partly they are self-sustaining. So that kind of agency helped us into scaling up the system. Coming back to your other very important question on water, water for life is, without water there's no life. And Kerala, you have plenty of water.
We are blessed with 44 rivers.
Rivers, and you are saying that
Backwaters.
36 of them are polluted. And if you say that 36, greater percentage of this pollution can be treated. Because when I looked at the data, 24 of this 36 are pretty much like organic contaminated water. They are not coming from industry. They are organic contamination, soil dumping, etc. And these things can be avoided with proper policies. And also there are very good institutions in Kerala, university institutions. They can do pretty much what I did with respect to deploying catalytic materials and systems. They need some scale up people to work on the scale up. Once they did this, then this can be doable here. It's not that it can be doable. Only the industrial contaminated water, about like 8 to 10, I think if I'm right, or 8 industries, they are doing quite a lot of heavy metals dumping. That heavy metals dumping needs to be addressed now, else it will spread as a carcinogenic wave.
So how can we address the industrial pollutants to the rivers?
I think there are quite a way, but putting stricter regulations and also asking the industry to adopt certain technologies and make investments, working with universities and others to make sure that they can start doing the proof of concepts.
And your group has also developed lithium ion battery recycling methods and upcycling methods also of the new materials generated from the battery waste in your work with IIT Hyderabad and Nile Limited in Telangana. So what we should learn, because Kerala has also this graphene or EV consortium like projects also.
Absolutely. See, if you look at this, the project is again kindly funded by the Royal Society, Royal Academy of Engineering, and eventually by UK and Indian government. This is on recycling lithium.
So everyone is going up to electric vehicles. So what about the batteries?
Yeah, see, there are
after the
these guys.
period?
There are more mobiles than human beings in this planet, and it is going to go much further with AI, etc. Every house has 3 or 4 mobiles, and they realize that there are precious metals there. Lithium is there, cobalt is there, nickel is there. There are precious metals, so we need to extract that. So that is the basic idea of this consortium. Then we co-developed, myself and IIT Hyderabad, we co-developed the technology, and the technology was given to a company in Hyderabad, and those companies they already made alkali batteries recycling. So now they are adapting that into lithium recycling. So it's not only recycling is important, you need to upcycle. Upcycle is a very important thing. What is upcycling is? So say for example, you have a graphite. The graphite, when lithium goes and percolates onto the graphite starts breathing. When it starts breathing, it's pretty much like this. Then graphite slowly starts exfoliating it. So we found a method to exfoliate that graphite into graphene, layer different types of oxides, graphene oxides, and then our graphite oxides, some of them are graphene. So you have mixed material there. That mixed material, we used our own printing methodologies, plasma printing methodologies, and then we started putting some new materials on that, and then to upcycle it and made it as a really good catalytic system. From the used battery materials, that went into our textile wastewater treatment. And some of them are also went to supercapacitors and batteries. So we can see where it started and where it's ended. So it is like we were thinking how we can create new physics and make new physics out of the existing batteries, and then deploy on to chemically functionalize them and make a different band structures, and then deploy into the wastewater treatment plant. So that is pretty much from the lithium cycling to end up in wastewater treatment plant.
Most of us think that hydrogen is our future fuel, but the storage and how we transport it to other areas, that's the main bottlenecks, I think. So what's your group's approach to that?
See, hydrogen storage is a 4 decades issue. It's not only now. So way back in 90s, people are talking about can carbon nanotubes can store hydrogen for transportation? Can we store with other metal oxides or MOFs, that is metal oxide frameworks, can they store? So it has been an ongoing issue, the storage, because hydrogen is kind of a lightest element.
And
And
it is
like,
highly.
yeah, and it needs high compression in order to store, like 350 to 700 bars to store the hydrogen compression. And also it diffuses easily. So if it diffuses easily to the metal, etc., and then it can easily be flammable. So it's very important to have a really good high-end technology, robust technology to do this. The cost is very high. I know that Kochi hydrogen something is there, I think, if I'm
Cochin
correct.
International
Yeah,
Airport producing green
green
hydrogen for
hydrogen there.
its
Yeah.
purpose.
So Cochin hydrogen is there, but can they afford this cost, high-end cost for the storage of hydrogen? That is another issue. Transportation is a similar issue as well. And if they say that, okay, I wanted to convert this hydrogen into ammonia and use that for the fertilizers, etc., that's another challenge also in the conversion. So there is a bigger issues are here. However, I feel that all these issues we can dwell, considering 600 million population of Indian youths are there and very high-end skills are there. We need to harness that skills to get some low-cost technology to get in realizable.
In your biodata, I saw that you once discussed nanotechnology initiatives with former president or people's president, Dr. APJ Abdul Kalam, and have lectured widely through DST Inspire. So, what core principles guide you for
Yep,
making
I think
fundamental physics serve real societal needs?
it's all comes from how we brought up as well. So we have been in that particular journey of self-learning to the PhD in Newcastle. I saw the different world of nanotechnology at the age of 2001, which we developed gold nanomaterials for different applications, etc. Then I was a bit intrigued, by probably went out of the way to write an email to the president, then president, former late Abdul Kalam, and saying that we have to do quite a lot on the nano, which we are not doing it. There are a few things I wrote. To my surprise, he returned back saying that he wants to meet me. And that's where our relationship started. And then I had really good interactions with him, and then working on different aspects of nanotechnology for education, and then how India can do implement those technologies, etc. So those discussions went into different routines.
Then another aspect is that you secured close to 80 million pound in funding. So that is also an issue in the research area or in the commercialization of research. So what's your advice to the researchers here in securing funding for the projects? Because in our country, the private funding is negligible, and the government funding is also lowest when we compare with the developed economies. So
No,
what would be your advice to secure proper funding for the research and the projects?
see, for the academicians, I think they wanted to generate PhD students, they wanted to do publications. And my sincere suggestions, not advice, is like we should not be in an era of publish and perish. You need to publish and process into products. And that is where that, as I said, I think it's third or fourth time I'm saying, it's like taxpayers' money needs to be utilized, and that people should see something coming out of it. And why I'm able to get work in the industry here, I work with UK Indian industries in some of the breweries. I recently visited some distilleries. Distilleries produces massive amount of wastewater, organic wastewater. So we are thinking of cleaning that wastewater and generating hydrogen. So they are happy to work. That is in Bangalore. They're happy to work with us. So the academicians generally, I'm not talking about only in India. In India, if you want to talk about Indian concept, there are plenty of money available in India. It is this thing of how you package it in such a way that you can reach out to the industry, and how your research can translate their bottlenecks. Wastewater treatment is a bottleneck. The process is a bottleneck. If you say that we are talking about plenty of startups coming out from IoTs, like Internet of Things and AI, etc. But that is the technology startups. How are the technologies are being incubated? Because there's not much push coming from the academicians to, yeah, we will take this challenge and you fund it. And there is the possibilities are there. There's a lot of possibilities. The current government, through ANRF funds, etc., they are opening up a plethora of opportunities. And it is doable. Only thing is that the way the academicians think has to change.
From Kerala, a large number of students going abroad for research and higher study, including the UK. So, what advice you would give Kerala students for selecting the universities abroad for their research and higher studies, as well as for jobs? So that, and for to those who want to have a research in material science, clean energy, or environmental nanotechnology, what is your advice?
So there are two-pronged situations. I've been in Kerala for fourth time now because of this project. One thing which I noticed, I travel a lot as well during this project time. So I noticed that Kerala has a bigger challenge of aging population. So people are migrating a lot within India, outside India as well. So if the same trend continues, I don't know, they will be having a huge expenditure in next 30 years in taking care of the aging population rather than in innovation and development. So when I compared Kerala with Switzerland, I think probably both are amazingly touristic place. Switzerland has IBM research, or IBM Zurich.
Kerala don't.
Kerala don't. Kerala has any big Tata's presence? I don't know. Kerala has big Reliance or Adani's presence? I don't know. So we need to have this. I think it is 90% or 99% literacy in Kerala, but these literate people are benefited outside Kerala. That is the main issues. So I think Kerala government has to do something very seriously at this time in order to incubate the local talents to stay in Kerala and do things. What we are talking about, hydrogen technology is one thing, solar energy is another thing. So there is lots of opportunities. To answer your other question, suggestions I would give for researchers, do choose your own supervisors and make sure when you are writing to supervisors that supervisors are really world class and they are keen to work with you rather than I really want to apply and go. Be choosy who you want to work, why you want to work, where is your end game. You should decide your end game before you start. End game is I wanted to do this kind of top end research, top end publications, and these skills I need to develop in order to go A, B, C, D skills. This is what the skills which goes into industries. So I wanted to prepare yourself with the end game rather than going with what you get. So that even if you wait for 1 or 2 years, please, my suggestion is please wait to make sure that whatever effort you put, it counts for the fruit. Rather than going again, I wanted to find jobs. And then you are going into the smaller circle saying that I wanted to get into jobs, which I'm not able to get. It's okay, but they are competing with millions. What is the uniqueness we can show? That uniqueness, a USP, you need to think through straight away.
Then where should the Kerala government would select a research or to make the most immediate visible difference in Kerala in the coming 5 years?
I think water
so
is
that
one thing.
we can solve much of the unemployment issues or any other.
No, I wouldn't say unemployment issues is easily solvable. I wouldn't say that. But if you want to quickly realize water technology is easy catch, which definitely some technology is already available, like biomass. Biomass is plenty. You have probably the half of the bananas you have in the world. You have plenty. Those banana has a nanocellulose. Those nanocellulose has a capacity to absorb. Then there's another thing called vetiver. Vetiver has a nanocellulose as well. Probably, I don't know here, people, if you go back 50 years, those grannies will give you that root, put it into the water, those water that immediately takes all the metals out, and then it gives a really good clean water for you. Those are all available in Kerala. So you need to harness what are all the different nanocellulose membranes or nanocellulose materials that can absorb water. And then you have plenty of researches going on nanomaterials and other combination of nanobiomaterials and systems that can be deployed and show that cleanness of the water. Once you show that, the people will excite. You need to excite science like Science Talk. You need to create excitement. That excitement is the one. More outreach needs to be done, pretty much like this. More outreach programs has to be done to ignite the minds of the young people. Okay, here it is the problem for you. Can you solve this? They challenge them. They like the challenge.
From material science to technology to sustainable development, your research has broken the walls of the lab and improving the quality of our life. Thank you very much for participating in Science Talk and finding time for us.
No problem. It's
And we-
absolute pleasure to be here, and thank you so much for your invitation. I hope I can share whatever message I can do. Particularly, science for society is important, and these kind of science talks is key in getting the outreach to millions and billions in this planet to make sure that the world is a better place to live in, and what we give to our children is more important than what we had. What we had is plenty, but we need to give the children more than less through science and technology. Thank you.
Thank you. This is Science Talk. Until next time, keep asking questions, staying curious, and building a better tomorrow.